Formal definition of similarity for polygons. Welcome, everyone. Before we dive into today's lesson, let's take a moment to reflect on what we've already covered. In our previous sections, we explored the intuitive, everyday idea of similarity, the notion that similar figures are simply those that share the same shape, regardless of whether one is larger or smaller than the other. However, as we move into more advanced geometry, we need to move beyond just looking at a shape. In mathematics, the phrase same shape is a bit too vague. We must define it with absolute precision. We cannot simply rely on a quick visual inspection and say, yeah, those look the same. To truly determine if two polygons are mathematically similar, we must move past our intuition and verify specific, measurable geometric conditions. In the next few slides, I will show you exactly what those two essential conditions are. The formal definition. Now that we've established that similarity is more than just a visual feeling of having the same shape, let's look at the formal definition. To begin, we must ensure we are comparing apples to apples, meaning the two polygons must have the same number of sides. If one is a triangle and the other is a quadrilateral, we can't even begin to discuss similarity. For two polygons to be officially called similar, they must satisfy two specific conditions simultaneously. This means both must be true at the exact same time. You cannot pick and choose. The first condition is the equality of corresponding angles. This means that if you look at the angles in the first polygon, the angles in the same positions in the second polygon must be exactly equal. The second condition is the proportionality of corresponding sides. Unlike congruence, where sides must be identical, here the sides don't have to be the same length. Instead, they must all change by the same scale. In other words, the ratio of each pair of corresponding sides must be the same. It is very important to remember this final point. If even one of these conditions fails, if the angles match but the sides don't, or if the sides are proportional but the angles are different, then the polygons are not mathematically similar, even if they look very close to it at first glance. In the next few slides, we are going to break these two conditions down one by one to see exactly how to apply them. Breaking down the conditions. Now that we have established the formal definition, let's take a closer look at what these two conditions actually mean in practice by breaking them down one by one. First, let's focus on the first condition, corresponding angles. When we are comparing two different polygons, we can't just pick any random angle. We have to identify corresponding parts. This simply means we look at the parts that occupy the same relative position in each shape. So, if we have polygon P1 that is similar to polygon P2, the angle located at vertex A in our first polygon must be exactly equal to the angle at the corresponding vertex, which we'll call a prime, in our second polygon. To make this concrete, let's look at a four-sided shape or a quadrilateral. For these two shapes to be truly similar, this equality must hold true for every single corner. This means that angle A must equal angle A prime, angle B must equal angle B prime, angle C must equal angle C prime, and finally, angle D must equal angle D prime. Keep this in mind, because while matching these angles is essential, as we will see in the next slide, it isn't the only requirement we need to satisfy. Proportionality of corresponding sides. Now that we have established that the angles must be identical, let's move on to the second and equally important condition, the proportionality of the sides. It is crucial to note that while the angles must be exactly the same, the side lengths do not have to be equal. If the sides were equal in addition to the angles, we would be looking at congruence, which essentially means the shapes are identical in every way. But for similarity, we are looking at shapes that are the same type, just different sizes. Instead of equality, we are looking for a constant ratio. This means that if you divide the length of one side by its corresponding side on the other polygon, you should get the same number every single time. This constant ratio is what ensures the figure has been scaled uniformly, meaning the shape hasn't been stretched or squashed in one direction, but has been enlarged or reduced perfectly. To see how this looks in practice, let's look at a quadrilateral. For these two shapes to be similar, the ratio of side AB over A'B' must be equal to the ratio of side BC over B'C', which must also be equal to the ratio of side CD over C'D', and finally equal to the ratio of side DA over D'A'. In the next slide, we will see how this principle applies to a real-world scenario involving architectural blueprints. Real-world example, architectural blueprints. Imagine you are looking at an architect's desk. An architect is designing a rectangular room, and to do this, they use a blueprint. If we think about this geometrically, the actual physical room is our larger polygon, while the drawing on the blueprint is our smaller polygon. Because the blueprint is simply a scaled-down version of the real room, these two rectangles are intended to be similar figures. Let's look at the specific measurements in this scenario. For our first polygon, which is the actual room, we have a length of 6 meters and a width of 4 meters. Now, looking at our second polygon, the blueprint, we see a length of 6 centimeters and a width of 4 centimeters. Now that we have established the theoretical requirements for similarity, specifically that we need both equal angles and proportional sides, let's step away from the abstract definitions and look at a practical, real-world application. At first glance, they look like the same shape, but they are vastly different in size. In the next slide, we are going to use the formal definition we just learned to mathematically prove whether this blueprint is truly a similar representation of the actual room. Verifying similarity in the example. Now that we have our scenario involving the architect's blueprint, let's put that formal definition we discussed earlier to the test. We are going to verify, step by step, if these two rectangles are mathematically similar. First, let's look at step 1, verifying the corresponding angles. As we know from our study of quadrilaterals, every internal angle in a rectangle is exactly 90 degrees. If we look at our actual room, all 4 angles are 90 degrees. Looking at our blueprint, all 4 angles are also 90 degrees. Because every angle in the first polygon matches its corresponding angle in the second, we can officially say the first condition of similarity, the equality of corresponding angles, has been satisfied. However, remember from our definition on slide 2, we cannot stop here. We must also satisfy the second condition. So, let's move to step 2, verifying the proportionality of sides. Here, we need to compare the ratio of the lengths and the ratio of the widths. Before we calculate, there is a crucial detail to note. We cannot compare meters directly to centimeters. To keep our ratios accurate, we must convert our units so they are consistent. Since 1 meter equals 100 centimeters, our 6-meter length becomes 600 centimeters. Now, let's do the math. For the ratio of the lengths, we take 600 centimeters divided by 6 centimeters, which gives us a ratio of 100. Next, for the ratio of the widths, we take 400 centimeters divided by 4 centimeters, which also gives us a ratio of 100. Notice how both ratios resulted in the exact same number. This brings us to our next slide, where we will conclude whether this constant ratio confirms the similarity of the room and its blueprint. Conclusion on the example. Now, let's bring everything together to reach our conclusion. If we look back at the calculations we just performed in the previous step, we can see that the ratio of the lengths, which is 600 centimeters divided by 6 centimeters, is exactly 100. Similarly, the ratio of the widths, which is 400 centimeters divided by 4 centimeters, also equals 100. Because these two ratios are identical, we have successfully satisfied our second condition, the proportionality of corresponding sides. So, to wrap up this example, we must look at the big picture. We have already verified that all the corresponding angles are equal, and now we have proven that the sides are in the same proportion. Since both of these essential conditions are met, we can confidently state that the blueprint is mathematically similar to the actual room. This confirms that the blueprint is a perfect, scaled-down representation of the real structure. Key takeaways. First, it is crucial to remember that similarity can only be discussed between polygons that have the same number of sides. You cannot compare a triangle to a quadrilateral and talk about similarity. They must be of the same type of polygon. Second, and perhaps most importantly, remember the dual requirement we've been focusing on. As we saw in our blueprint example, similarity is not a pick-and-choose situation. It requires both equal corresponding angles and proportional corresponding sides. As I mentioned earlier, meeting just one of these conditions is simply not enough to claim similarity. Third, let's look at the mathematical notation. When we want to state that polygon A, B, C, D is similar to polygon A', B', C', D', we use the tilde symbol. We write it as A, B, C, D is similar to A', B', C', D'. This symbol is our shorthand for saying all those conditions we just discussed are met. Finally, keep in mind the concept of scaling. When we say the sides are proportional, what we are really saying is that the figure has been enlarged or reduced by a consistent scale factor. This is why the shape remains identical even though the size changes. All right, let's wrap up our lesson by summarizing the key takeaways from today's discussion. Now, before we finish, I want to point out a few common pitfalls that students often encounter, so please pay close attention to the next slide. Common mistakes to avoid. First, a very frequent error is assuming that equal angles are enough to prove similarity. It is tempting to look at two shapes, see that their \text angles match, and stop there. But remember our dual requirement from earlier. For instance, think about a square and a non-square rectangle. Both of these shapes have four angles that are all 90 degrees. However, they are not similar because, as we discussed, their sides are not in the same proportion. On the flip side, do not assume that having proportional sides is sufficient on its own. Consider a square and a rhombus. In a rhombus, all four sides are equal, just like a square, so you could argue the sides are proportional. But a rhombus can have very sharp or very wide angles, whereas a square must have 90-degree angles. Because the angles don't match, the similarity fails. Finally, always be careful with your pairing. When you are calculating ratios, do not just pick any side from the second polygon. You must be systematic. Always ensure you are comparing side AB with its specific corresponding side, A', B', and so on. If you pair them incorrectly, your entire calculation will be invalid. Now, as we wrap up this lesson, I want to highlight some common pitfalls. Even students who understand the definition can sometimes fall into these traps during exams, so please pay close attention. Keep these points in mind, and you will be able to approach similarity problems with much greater precision.